Hello everyone, and welcome back to Educator.com. In this lesson we're going to talk about RC circuits, but specifically about the transient analysis. What happens as a function of time in these circuits. So our objectives include calculating and interpreting the time constant, tau, of an RC circuit, sketch or identify graphs of stored charge or voltage for the capacitor or resistor, write expressions to describe the time dependence of the stored charge, voltage, or current for elements in an RC circuit, and analyze the behavior of circuits containing several capacitors and resistors. Now, as we get into this lesson, please understand this one's going to be pretty math heavy. The transient analysis of RC circuits is one of the more challenging portions of the E&M course. So this may get in-depth a little bit, probably a great time to pause, to go back, to take really good notes, and you may have to come back to this one a couple times. It's not easy stuff, and the first time you see it, it looks like there's a lot of math involved. What you'll find as we go through is you'll see a bunch of the same patterns repeating and repeating. But the first time you see it, it can look a little bit scary. Don't be daunted, you can get through it. All right, so let's take a look at what happens when we charge an RC circuit. So here I have a basic RC circuit. We have our source of potential difference, resistor. We've defined our current direction, our capacitor with the voltage across our capacitor, and at time t equals 0, we're going to close the switch. We also have graphs down here of current in the circuit, charge on our capacitor, and the voltage across the capacitor that we're going to be filling out as we go through here. So we've done these before, but let's take a minute before we get heavy into the math just to think about what these are going to look like. We know the current in the circuit initially is going to be high because the capacitor acts like a wire. So we're going to have all the current, I equals Vt over R. So we're going to start here at this high level of current. And by the time we get to roughly 5 tau, the current's going to dwindle down to less than 1% of its initial value because our capacitor starts to act like an open. So our graph is going to have an exponential decay, something like that. The charge on our capacitor is going to start at 0. It's uncharged, and after a long time, that being again 5 tau, it's going to be CVT. So we'll have an exponential rise toward that asymptote. And the voltage across our capacitor starts at 0, acting like a wire, and over time approaches VT. So our graphs should look something like that. Our goal here is going to be to mathematically describe those by actually figuring out what happens rather than just quick estimations. So to do that, let's start by looking at Kirchhoff's voltage law. And we're going to do that. I'm going to start down here and go clockwise around our circle. So as I look at our potential drops, I see minus VT first, plus IR, plus the voltage across our capacitor brings us back to our starting point. So all of that must equal 0. But we also know here that C equals Q over V. Therefore, V equals Q over C. So I can rewrite my equation now as, let's rearrange this a little bit too, VT is equal to IR plus, I'm going to replace VC with Q over C. This implies then, though, Q and I are related because I equals dQ dt. We can write this as Vt is equal to R times dQ dt, replacing I with dQ dt, plus we still have our Q over C. We have a differential equation. We have Q and the derivative of Q in the same equation. So how do we deal with something like that? Well, the first thing I'm going to do is called separation of variables. I'm going to try and get all the variables of the same type on the same side. So I need to get Q and dQ together. So this is going to take a little bit of algebraic manipulation. And the reason I know how to do this is I've done it quite a few times. You really just have to practice it and dive in and do it again and again and again. So let's rearrange this. I'm going to get dq dt all by itself by dividing both sides by r. So I will have Vt over R equal to, we have our dq dt plus q over rc. Right, and rearranging this again, trying to get all our q's together, I'm going to write this as dq dt is equal to vt over r minus q over rc, just a quick algebraic manipulation, which implies then that dq dt equals, well, I can multiply c down here to combine these on the right-hand side, give us a common denominator of rc, so I would get c vt minus q over rc. And now getting those variables separated, I have dq over c vt minus q must equal dt over rc. So just a little bit more algebraic manipulation. I have my q's on one side, I've got my variable t on the other. That means I can go and I can try and integrate both sides. Not try, we're going to. So, integral of both sides, we'll take the left-hand side first. The integral in our variable of integration is q, which is going to go from some value 0, initially the charge on our capacitor is 0, to some final charge q of dq over cvt minus q must equal the integral of the right-hand side, dt over rc. But our variable of integration on the right-hand side, t, goes from some initial time, t equals 0, to some final time, which we're going to call t. All right, as we integrate this, the left-hand side, we've got a problem of the form du over u, and the integral of du over u is natural log of u. Now we've got du over minus u, so we're going to get minus the log of, what do we have, cvt minus q evaluated from 0 to q. And the right-hand side, well, 1 over rc is a constant, so we're just going to get t over rc evaluated from 0 to t. All right, a little bit more algebra. This implies then that, well, we'll substitute in our values, our limits here, minus the log of cvt minus q minus the opposite of the log, which is going to be plus the log of cvt minus 0, which is just cvt, equals t over rc. Which, if we've got a difference of the logs, log of that plus log of that, we can say that we have the log of cvt minus q over cvt equal to, I'll move that negative sign over here to the right, minus t over rc. All right, so we can simplify this left-hand side a little bit too. So that means that the log of, well, that could be 1 minus q over cvt equals minus t over rc. And I'm starting to run out of room, so let's carry this over onto our next screen here. All right, we have the log of 1 minus q over cvt equals minus t over rc. This log is troubling. How do we get rid of a log? We take e and raise it to that power. So e to the log of 1 minus q over cvt is what we're going to do. Raise both sides to that. So e to the log of 1 minus q over cvt must be equal to e to the minus t over rc, doing the same thing on both sides to maintain that equality. E to the log of something is just that something. So our left-hand side gets a little simpler. We have 1 minus q over cvt equals, right-hand side, e to the minus t over rc. All right, well, let's see if we can't get rid of that 1 on that side and do a little bit of rearrangement to say that q over cvt equals 1 minus e to the minus t over rc. which implies then that getting just Q by itself, Q as a function of time, is equal to CVT times the quantity 1 minus e to the minus t over RC. We were able to solve for the charge on the capacitor as a function of time. And when you do these types of problems, you're going to see very similar forms come up again and again. Some constant multiplied by either 1 minus e to the minus t over RC, or just that constant times e to the minus t over RC. You're going to see this come up again and again and again, to the point where you can almost predict the answer before you go and actually solve it. Well, if that's our charge, let's see if we can't find the voltage across C. VC equals Q over C. Well, we just found Q was CVT times 1 minus e to the minus t over RC, all divided by C. So then our C's make a ratio of 1. We get that the voltage across our capacitor, our potential difference, is just VT times 1 minus e to the minus t over RC. Okay, well, how about current flow? Well, the trick to getting current flow then is realizing that I is the current is equal to the derivative of the charge. So current I is dq dt, which is the derivative with respect to t of our q, which was CVT times 1 minus e to the minus t over RC, which is going to be, well, we can pull our constant out, minus c VT times e to the minus t over RC times minus 1 over RC, e to the u du, where du is minus t over RC. So the e to the u du, the derivative is minus 1 over RC, excuse me. So that's going to be, let's see, CVT over RC times e to the minus t over RC, which implies then, well, our capacitances, C's are going to make a ratio of 1, that our current then equals VT over R e to the minus t over RC. Oh, but by the way, VT over R, that was our initial current. So I is actually equal to its initial value times e to the minus t over RC. So we were able to find the values for the current, the voltage, and the charge on the capacitor, all as functions of time, much more exactly. And you see this exponential relationship over and over again, where again, RC is your time constant tau. So sometimes you'll actually even see this written as, instead of e to the minus t over RC, you'll see it written as e to the minus t over tau.